All right, cool. So welcome to office hours for 4:30. I'm going to work through the lab quickly. I have some students in the chat with me, so if you hear other voices, those are the students who are here. Thanks to you all for being here. So we're just going to work through the lab. So I have a file open here. So I'm working on Stu, by the way, and I would recommend working on Stu for this. You can get it installed locally, but I've found that students, especially if you're using Windows, there are some issues with using Prolog. So I recommend just going to Stu if you can. So I've got a file on the left, which is where I'm going to write all of my rules, and then I have an interactive terminal here. So the big thing that we're introducing this week for Prolog is lists. And so, you can write lists in Prolog, or sorry, you can write lists in Prolog the exact same way that you do it in a lot of other languages. So this just sort of instantiates X with a list. The syntax, so whereas in Haskell we would have done something like 1, 2, 3 empty list. So in Haskell, this is what we would have done. In Prolog, the way you would do this is to use the pipe operator. So that separates a head from a tail. And I believe you can use it like this, and you might have to include some extra ones. So obviously it gets a little cumbersome to use that notation, but that's the notation that we're going to use for pattern matching. So the lab kind of walks you through looking at this. So the example that the lab has you do is, we have the list 1, 2, 3, 4 here, and if we pattern match that against A pipe B, then A gets instantiated with the head of the list, which is a single item, and then B gets populated with the tail of the list, which is the list containing everything except for the head. So that's similar to how it would be in Haskell, so it's just a slightly different notation. All right, so we're going to start by defining the size predicate that counts how many items are in a list. And again, there are a couple of different ways of thinking about this. So you can think about this as being a predicate that counts the number of elements in a list, or you could think about it as a predicate that is true when its second parameter is the length of a list. So for instance, one thing that we want to be true is that we want the size of an empty list to be 0. And that's how we would say that in Prolog, is we would just make the statement, this, size predicate when the first parameter is empty list, and the second element is 0, that is true. So the way to read this is that the size of an empty list is 0. So if we were to read this in, now we can check this, and we can say, well, size of 0 is true, or size of the empty list is 0. That is true. And we wouldn't be able to do this yet, so that's still going to be false. And so what we need to do is we need to write a recursive definition for that, and we just gave that to you in the lab. So we're going to say that for any other non-empty list, so a non-empty list is going to have some head and some tail, and I would actually recommend, the lab doesn't have you do this, but I would actually recommend writing out lengthier variable names, at least at first, until you get comfortable with this. The first character has to be capitalized for it to be a variable. The rest doesn't have to be. So we can write the definition like this. So the size of some list that has a head and a tail is going to be in. So this is, or I guess we should say that this could be, size, right? So this is true if, here's where we have to use the recursive definition. So we know that the size of this list is going to be 1 plus the size of the tail. So we can state that. We can say that, well, size of, and I don't want to use size for both of these. So let's call this length. So this is going to be true if the size of tail is tail length, and length is, and here we have to, I'm going to define this on multiple lines here. So here, length is tail length plus 1. And I think I can just write it like that. This is not exactly what's in the lab solution, but yeah, do I have to? Yeah, I might have to do it all in one line. That's, oh, no, something else is going on. Let me just paste in what I had in the lab. I was trying to make the variables a little bit easier to see. Oh, and I just noticed that my syntax highlighting isn't working. Okay, there. So now it knows it's a Prolog file. So is this working? Oh, you know, that would be a dumb mistake. All right, cool. So I think that was probably the problem, is that I didn't have a period. All right, cool. So this is our definition for size. So the size of an empty list is 0. The size of any other list that consists of a head and a tail is length, where length is tail length plus 1, and tail length is the size of the tail. So hopefully this is maybe a little bit easier to this definition might be a little bit easier to understand than the one that's in the lab. Is there anything else I want to note here? We get a warning over here, and this is not a new thing. We've run into this before. There was actually a Piazza post about it 2 weeks ago. This is just saying that head is given a name here, but we never actually use that name. So nowhere else in this definition do we use head. So really, we could just avoid giving that variable a name, and we use the underscore to do that the same as we would in Haskell. So now the empty list is of size 0. The list 1, 2, 3 has size 3. It does not have size 4. So remember, we should always test negative cases as well. And if we wanted it to go and find the size, we would leave that unspecified, and then it would go find the X for which this is true. Okay, I'll pause there for a second. Are there any questions? Does that definition make sense? I know that that's the very beginning of the lab, and people may have kind of breezed through that, but I want people to have I want them to be more comfortable with the definitions at this point. So if things were a little bit loose the first time you worked through it, I want it to be, I want it to make sense this time. All right, hearing no questions, we'll just keep going. Okay, so the next one is an end predicate. So in other words, end LX. So this needs to be true if X is the last element in this list. So we're going to introduce the notion of a predicate failing at this point, because we need to say something about the end of an empty list, right? There is no element in an empty list, so this predicate should always fail. There is no way for this to be true, and that's how we would encode that in Prolog. So another easy case to handle is if there is a particular, if the list contains one item, so that's this case right here. So we have a list containing one item. Well, that item is the last item in the list. So we can go ahead and make that definition as well. So we can go ahead and test this over on the other side. So we'll go ahead and load it in. So it's giving us that singleton warning again, because we haven't finished this definition over here. And actually, I should probably comment that out. All right, so now at this point, we can say, the end of an empty list is always going to be false. If we have a list containing only one element, it's going to be that one element. But then if we have a list with multiple things, we haven't written a definition for that yet. So what should that look like? Well, the end of any list where, let me pull this over here so that I have it more easily accessible. I've got the solutions up over here so that I don't go off the rails. All right, so the end of any other list, so it has a head and a tail. Don't do what I almost did, which is separate them by a comma. You have to use the pipe operator there. So the end of any other list where there is more than one element in the list, that's just going to be the head of the tail, right? And we have to encode that. Well, we have to encode that here. We have to say, well, this is true if the end of the tail is, head of tail. And again, we're going to get the singleton warning when we import this because we haven't used head over here. And in fact, we don't need it, right? The head is of no use to us when we're trying to grab the last item in the list. So we can just avoid giving it a name. And now we can do this, and it will find that 7 is the last item in the list. It's actually asking us if we want more than one item in the list. And so this is never going to give us anything. The last item in the list is always the only last item in the list. And so one way that we can kind of encode that is to say, all right, as soon as you find one of these things, go ahead and stop, because there's no way that you would ever find a different one. That's just the way the Prolog does its search. It gets to this point and thinks that there may be something else. All right, does that make sense? Any questions about that? All right, so then we want to write a predicate that finds the maximum value in a list. Again, this should also fail for the empty list. So we'll go ahead and encode that. So the max of an empty list is always going to fail. There is no greatest item in an empty list. The definition for a list with a single element in it is going to be exactly the same as end, because the maximum element in a one element list is always that element. So then what we want to do is we want to think about the maximum item in a list that has a head and a tail. So there is an item called head, and then there is an item called, or there is a list called tail. So there are actually two cases here if you think about it. The first case is, well, maybe the head is the maximum item, or maybe the head is not the maximum item. So we're actually going to do two separate cases for this. So the first case is if the head is the maximum item. So we need to encode the conditions under which that will be true. But we can go ahead and think about what we're going to need to do for the other condition. So in the other condition, the maximum item is actually the head of the tail. So these are the two these are the two predicate definitions that we need to finish here. So under what condition, how would we describe the conditions under which the head is the maximum item across the entire list? Well, if you think about it, you need to be able to say that head is greater than the maximum item in the tail, right? So we will need to go ahead and give that a name, and let's go ahead and write that first. So we'll say max of tail is, and actually it's not head of tail, actually, that's wrong. It would be the max of tail. So sorry for writing that down incorrectly at first. All right, so the head is the maximum element. If we go and look at the tail and we find the maximum in the tail and head is greater than the maximum of the tail. So that is the condition under which this is true. So let me see if I can make this window a little bit bigger. Okay, cool. So then hopefully it's not too hard to see that the other condition, we still need to find the maximum of all the rest of the elements in the tail of the list, but then the condition is going to be switched. So if the head is less than or equal to, and I think you may have to do this, yeah. So that's just a weird thing that Prolog does. You have to put the equals first. Okay, so if that worked, now we should be able to say max, and it will calculate the maximum element. And again, we might want to run a cut on this just so that it doesn't think that we can find more than one maximum of a list. And we should probably run another test here to make sure that it can identify the maximum element when it's in the middle of the list, which it can. And then we should make sure that this works for a single element list. And again, we might want to cut there as well. Oops. Oh, that's interesting. Adding a predicate just for the cut. Cool. Okay. Does that make sense? Questions about that? Okay. So the next one is evens. So we want to extract all of the even elements, even numbers from a list. So an even number is divisible by 2. And so in Prolog, we would do this by saying, well, so normally you would do something like, well, x mod 2 equals 0, right? This is normally the condition under which something is even. So in Prolog, we're going to write this as 0 is x mod 2. So that's just the way that you would encode that in Prolog. So given that, then let's think about the cases that we care about. So what are all of the even numbers in an empty list? Well, there aren't any, right? So the answer is just going to be the empty list. So this says that there are no even elements in an empty list. So the more interesting cases are, or the more interesting case is, well, what if there is a head and there is a tail? What is the list of all of the numbers? Well, I guess the question here is, well, is head even? If head is even, then it needs to be in this list. If head is not even, then it should not be in the list. So again, we kind of have two cases here. We have one case where head is in the list, and we haven't really figured out what the tail is going to consist of. So that's one case, and so we'll need to encode when that's true. And then we'll need to encode the case where head is not an even number. And so this question mark here, if you think about it, is all of the even numbers from the tail. So we can give that a name. So evens from tail. So this is what we want. So we want to have two cases where if head is even, it is in the list, and if it is not even, then it is omitted from the list that we build. Okay, so we will want to encode our condition here. So so this is the one that should be true if 2 is even. So 0 is head mod 2. And then we need a condition about evens from tail, right? So we want to say that all of the even numbers in tail have been extracted and they are evens from tail. Do I want to make the screen even bigger? All right. Actually, I might just. Are we comfortable abbreviating names at this point? Because that would mean we don't have to make these things so big. Let's go ahead and start abbreviating names. So evens from tail, let's just call this all right. I think Tmux was not playing nicely with Bim. Okay, there we go. All right, so let's call this tail evens, or TE. TE is going to be the even numbers in the tail. So 1 is head mod 2, so that's going to be true if head is odd, meaning that we don't want to include it, which is what this condition is encoding. And then we have the same condition here, which is that we want to pull out all of the even numbers from the tail, and that becomes our new list of evens. So we should be able to run this now. So evens in an empty list is an empty list. Evens in a list containing one even number will give us that number. An odd will give us, whoops, 8 is not odd. An odd number will, a list containing only one odd number will give us an empty list for evens. And then if we have a bunch of numbers, this will pull out the even numbered ones. And again, we could add some cut operators if we wanted to not have Prolog do this business where it attempts to calculate multiple solutions. Okay. So the last standard function here is concatenate. And if you remember, do I have that easily accessible? The concatenation from Haskell, I don't think I have that easily. So I don't want to waste time trying to bring that up. But this definition may look somewhat similar to that. So this is now a 3-element predicate, so concatenate, if I can spell it correctly. So if we have, so the way this works is that we have a predicate A, B, and C. So this is going to be true. This needs to be true if, C is A concat B. So in, Haskell notation, we could use the concatenation operator. Prolog does have a built-in concatenation predicate, but we want to write it from scratch just to see what it would look like. So C is the concatenation of A and B. So if we think about this a little bit, we can think about the different cases here. So what we're going to do is we're going to kind of recurse on A, because we build lists by taking a single item and making that the head of a list, and then taking another list and making that the tail. So what we kind of want to do is recurse down through A and slowly tear off items from A and put them into a new list where we're recursively building that new list. And so the base case is going to be when A is empty. And if A is empty, then C is just going to be B, because there are no more elements in A. And so the concatenation of an empty list and any other list is just going to be that list. So that's the first part of our definition. And then the other part of our definition is, well, we have some element of A. So let's call that element A, EA. Or we could just call it A. And then we have some tail of A. And so that's going to be the other case here. So if there is some element A, and then there are more elements in A, what we want to do is, and then there's B, we want to say that C is a new list where we have A at the beginning, and then we want to recursively concatenate T and B. And we can express that, so we can write a new variable here. So I don't know what we want to call it, but this is sort of the tail of C. So if this is the tail of A, TA, this is going to be the tail of C. So this is true. Let me put in some commas here to make this easier to read. So this is going to be true if, so this is just always true. And then this is going to be true if, so the condition that we need to express here is that we have concatenated TA and B to get TC, which we can do recursively. So TC, well, actually, we would just state this using the concatenate predicate. So concatenating TA and B gets us TC. All right. Oh, I probably forgot another period. Oh, this is. All right, cool. So now we can, concatenate. So let's exercise our base case first. So if we have an empty list for A, that will just give us B back. And then if we have any other list, this is going to pull elements out of A, make those the head of this new list that we're making, and sort of do that recursively. And then when we get down to B, it'll be the base case again, and we'll just get all the elements of B. Okay, so that is the, so those are all of the list functions on their own in the lab. And then there is this whole binary search tree thing. But what I'm going to do is pause now and see if there are any questions. And actually, at this point, I'm going to turn off the recording so that the folks in chat feel a little more comfortable talking. And then I'll turn it back on when we start working on the rest of it. So